Hey, hello and welcome back everybody. So we're moving on to section 2.5. I'm calling this the common rules of discrete integral, but if we recall kind of from the last video, the discrete integral really was just the sum, or in our notation with this capital sigma, it was this object. I would put an n underneath and some sequence inside of the summation symbol, and this was equal to some capital A sub n, where if you took the finite difference of capital A, you recovered lowercase a sub n. So just like with the other common rules section we've had, I'm going to start off with really just a table of all of our summation rules. And now that we know what the summation symbol means, we can actually condense a lot of our formulas quite a bit using that symbol. You can tell in some of these, like the by substitution, there's actually an extra term of a summation in certain parts. Similarly with this first power rule, we've got an extra summation sitting in there. So we can actually use the kind of the definite summation notation to help us define our rules. But we do have these indefinite sums on the far left. So we covered linearity at the end of the last section, and linearity, as always, just means that the symbol, or really the action of this object, the action of summation, can be distributed over addition, and actually it even commutes with these constants C1 and C2. So the C1 and C2 can come to the outside, and the summation has distributed, so I'm just acting it on, the sequences themselves on the inside, AN and BN. So there's those two sequences that I'm going to sum. That was linearity. We've got something called a telescoping sum that we'll go over a little bit later. What this says, if I take the sum of a difference, right, so this is the sum of a difference of a sequence and its shift. What do I mean by shift? Well, if you look at the second sequence, I've taken the subscript and I've shifted it by k, so this is some number that the subscript has been shifted by. Then there's a formula for kind of the output of this sum, and we'll go over that a little bit more later. We've got a summation by substitution. I do provide the full notations here for that. It's really quite ugly, so we don't worry about it. It's saved for the appendix. We're not going to actually use it as a rule in this book, but actually it's quite the common question that students will ask me if it's even possible, since summations really are a version of integration. It's possible, but it's really quite ugly. We have something called reindexing, and this is an incredibly common technique used in Calculus 2. Reindexing is the act of shifting just the inside of the sum, right? So we've shifted the sequence within the sum. And if we reindex on the inside, that's where I've shifted by k. On the inside, you can just reindex on the outside. So if you compute your kind of anti-finite difference, capital A, you can just shift that as well. So reindexing is useful because it lets you shift back and forth all of your rules. If you notice some summation has a shift built in or vice versa, and you want to get rid of a shift. Summation by parts is going to play the same role that integration by parts played, and it's actually going to look quite similar to integration by parts. Here we've got the summation of a product. We're going to end up with integrating one of the terms of the product, keeping the other term, and then subtracting the summation of the integrated term times the derivative, or really the finite difference of the other term. There's a very slight caveat in terms of summation versus integration, is that this integrated term has now been shifted by 1. You've probably seen this a lot when we've gone into the discrete calculus in the quotient rule for the finite difference. The denominator wasn't the old denominator squared. The denominator ended up being the product of the old denominator as well as its shift by 1. So because of the way the finite difference works, you do often see these shifts by 1 in terms that you wouldn't see in the continuous calculus. Then we have our power rules. And this first one is absolutely atrocious. I mean, it was atrocious in the finite difference setting, but in the anti-finite difference setting, which is the summation setting, it's extra atrocious. So we've got these things called Bernoulli numbers, which are really quite a fascinating topic in and of themselves that unfortunately we don't get to go into. They have a formula, right? We've provided the formula here at the bottom. The formula for the Bernoulli numbers themselves consists of 2 summations. And then the formula for the power rule consists itself of yet one more summation. So there's like 3 summations going on to compute the single summation that is the first power rule. We will go through a couple examples of these, but you really shouldn't. You shouldn't think about summations of traditional powers or traditional monomials like this. And that's what I was trying to hint at in the previous, well, it's really 2 sections ago, but the section on finite differences where I said we had 2 power rules and we defined the falling factorial. Let's recall what the falling factorial is. N falling factorial k is defined by n times n minus 1 times n minus 2, and you keep multiplying until you end up at n minus k minus 1. So you stop 1 early from reaching k subtractions. But what that gives you is k total terms. in the product, and that's the falling factorial. It turns out that that power, it's not exactly the same power, it's a different polynomial. If you expanded this, you would get a polynomial of degree k. So it's a different polynomial of the same degree that, you know, the traditional monomial would be of, but it's defined this way, and really this is how we should think about powers in like discrete land. And it turns out then if you think about power rules for falling factorials instead, they look exactly the same as the integral. So it's the same as the integral power rule, but we just have to modify how we're interpreting this name, power. Power is all of a sudden the falling factorial to us. Our exponential rule is quite straightforward. We just have the summation of a to the nth power. It's going to be a to the nth power, but you of course have to divide by that a minus 1, which showed up when you took the finite difference as a multiplication term, so it's going to be a division term when you take the anti-finite difference. And the logarithm rule is quite interesting actually. If you take the sum of a logarithm, you end up with the logarithm of a factorial. So it's very interesting. So the summation of log is log of really shifted. We've been shifted down by 1 factorial. And why have we been shifted down by 1? Let's recall really quick that you can define an anti-finite difference really as k starting at some minimum value up to n minus 1 of this lowercase a sub n. So you could define it as that definite sum, and because that upper bound is n minus 1, that's where this n minus 1 in the log is coming from. So we'll actually spend more time on all of these rules. I just kind of wanted to get through the table. Got a comment about there not really being useful trig rules or inverse rules. We just, the discrete calculus doesn't behave quite as well, at least in closed form, as the continuous calculus, so we just can't go into quite as much detail with all of our rules. But I provided the ones that can be used, and if you pay close enough attention to that table, everything does work out pretty well for you. It's just sometimes you have to be pretty meticulous to make sure it works. We're going to start with the first one that's kind of non-trivial here, and that's the telescoping sum. And a lot of times when students learn the telescoping sum, they just learn this bottom case. This is the simplest case, but I've provided it because it's the most common learned ones. This is the simplest case of telescoping sums. And what does it say, at least in the simple case? Well, it says if I take the sum of a sequence minus its neighbor, right? That's how we can think about this. This is a sequence minus its neighbor. So sequence minus its neighbor, it ends up just giving the neighbor itself. So it gives the smaller of the two terms. Plus c, everything is unique up to a plus c here, right? So how else can I think about this? Well, what's going on the left-hand side? That is really just delta of a n minus 1, right? The way that the finite difference is defined, that is delta of a n minus 1. Here I'm taking an integral of a derivative, so the integral of the derivative cancel, and we're just left with a n minus 1. So this is really how you should think about the telescoping sum, but you have to be clever in recognizing it, right? This won't necessarily be presented to you as a finite difference. I'll say that won't necessarily be presented as a finite difference. And so because it's not presented as a finite difference, you kind of have to take that upon yourself and recognize that we have some sequence minus its neighbor. And once we realize that you have a sequence minus the neighbor, then we can call it a telescoping sum. What happens in kind of the full statement, which is what I have above, you can see I've got a sequence minus its neighbor, but the neighbor's been shifted by a substantially larger amount than just one term. So you can really think about this as a sequence minus its kth neighbor, right? Or, k houses down from where you live, right? That's what this minus k is saying. So you're starting somewhere and then you go k terms away. And the price you pay for that is actually a sum. So you have to take this is now a definite sum of k terms, right? Because I'm starting at j equals 1 and going up to k, and then I'm just going to plug that j equals 1 all the way up into k. So if I were to write that definite sum out, individually, it would be an minus 1 plus an minus 2 plus an minus 3 plus ... plus an minus k minus 1 plus an minus k. So it's going to be, k total terms that get summed together. And then the n's, of course, the n is still your variable. So all of these n's are playing the role of your variable. There's a proof here. It's called telescoping for the same reason that if you were to actually grab a telescope, I'm going to do my best to draw a telescope here, just like in pirate times. Suppose you were looking for land off on the horizon, and here's your beautiful telescope. Then you can look into the telescope, but maybe you're done looking into the telescope, and what do you do so that you can save a lot of space is you grab the front of the telescope, you grab the back of the telescope, and you push them together, and what happens at each of these breaks is that they all collapse in, and you end up with kind of a single telescope, condensed telescope that really looks like this object, and you've just got all these that have kind of crashed in on themselves except for the very front. What you've got here is a n minus 1, that was a little typo at the end there, and really all the way down to this a n minus k term, if we've subtracted by n minus k, you think about this as the front of the telescope. And then everything else that's left over here, like a0 up to a n minus k minus 1, because the original sum had a subtraction in it, you can distribute using linearity the sum to both terms, and it turns out that the second case, kind of the back of the telescope, is exactly subtracted off. Or you can think about this as the collapsing. So it collapses, and all you see is the front of the telescope. So what you're actually left over is just the terms that remain in the front of the telescope, which just looks like a sum of the terms following an minus k. That's where the term telescoping comes from. It looks even better if you go ahead and do it with a single shift rather than k shifts. And then I think it's important that we also talk about definite telescoping sums, because in reality, this is what a lot of undergrads learn when they learn about telescoping sums. In particular, as I was mentioning before, they often learn, and I'm going to enforce here, that you kind of recognize this case where we have a sequence an subtracted by its neighbor an minus 1. In the case of a definite telescoping sum, this is where I've put bounds on there, it actually gets quite easy, which is why it's often taught. You take the larger of the two sequence terms and you evaluate on the upper bound, so that's going to give you an max. And then you take the smaller of the two sequence terms and you evaluate that on the lower bound. That's going to give you minus an min minus 1. So this is really the telescoping sum result that you would want to learn for kind of the future, the rest of your life maybe, if you're going to be asked to evaluate sums in any particular way. Now, of course, we also have the telescoping sum situation where we've subtracted not by the single neighbor, but maybe k neighbors down from where we started. That's going to be the upper case, and it's just a little bit more complicated because we're still going to evaluate kind of the top sum at the top bound. As you see that here, an max, and actually if I would evaluate this definite sum on the right-hand side at j equals 1, you can see that we'd have an max. We're going to add 1 to that, but we're actually going to subtract 1 from that as well. And so you do have that very top term of an max, and you also have the bottom term, an minus k, evaluated on n min. You can imagine when at the end of this definite sum, when we have j is equal to k, that second term is going to be minus an min minus k, but we do have to play the games of basically this adds all terms between the top one, which is an max, and the bottom one, which is really negative an min minus k. So it's going to add all of those terms there. We'll see how to apply both of these in the next example, because these definite sums are the ones that you really do want to learn when it comes to telescoping. So next example, we're going to take the sum starting at 1 and ending at 10 of 1 divided by n squared plus 3n plus 2. You can imagine in this case, we've got a definite sum here starting at 1 and up to 10. Because it's a definite sum, if we wanted to, we could totally just evaluate this at, plugging in each case of n on the inside. We have 1 squared plus 3 times 1 plus 2 plus 1 over 2 squared plus 3 times 2 plus 2 plus 1 over 3 squared plus 3 times 3 plus 2. We would keep adding, right? And our second to last term would be 1 less than 10, so 9 squared plus 3 times 9 plus 2, and then the final case, 1 over 10 squared plus 3 times 10 plus 2. But that would be a heck of a lot of work to shove into a calculator. Certainly if you had a computer and you were coding this up, you can make it a little bit easier than that. But we can actually do this by hand. Because of telescoping sums, we know how to evaluate this by hand. We have to go through a little bit of work to find out how. This is a technique that you're going to discover later in this book. This is still that partial fractions decomposition. So don't worry about it right now. I'll say we will learn this simplification later. But you can actually rewrite 1 over n squared plus 3n plus 2 as the sum, or really the difference, 1 over n plus 1 minus 1 over n plus 2. And when you write it like that, if I rearrange it a little bit, I'm going to bring the 1 over n plus 2 to the left and call it really negative 1 over n plus 2. And I'm going to bring 1 over n plus 1 to the right. What is n plus 1 in terms of 1 over n plus 2? It's really 1 over n minus 1 plus 2. And now it makes it clear we've got an n here, we've got an n minus 1 there. That's really playing the role of a sub n minus a sub n minus 1, because I've replaced the n on the left with an n minus 1 on the right. The moment I recognize that as a difference of a sequence an with its neighbor an minus 1, I know that I can just rewrite up top here, this is going to be the sum n going from 1 to 10 of an minus 1. And if we use that corollary we just covered, when it's kind of the simplest case where it's the true neighbor, we're just going to evaluate an on the upper term, that's giving me a10, and we're going to evaluate an minus 1 on the lower term, that's going to give me minus a1 minus 1, or also known as minus a0. So we're going to evaluate those specifically when a is this negative 1 over n plus 2. And when I do that, I've evaluated, here's a subscript 10, I've evaluated 1 over n plus 2 at 10, I'm going to subtract negative 1 over n plus 2 at 0, and I'm just going to simplify everything. You find out you get 5/12 out of this sum. Second case is going to be a little bit trickier, provide a second example for us. We're going to take the sum from 1 up to 15, 1 over root n plus 1 plus root n minus 1. And we're actually going to be able to figure out that this is a telescoping sum by rationalizing the denominator. If it maybe weren't clear why this were going to be a telescoping sum from the beginning, it's not perfectly simplified right away. So we're going to want to rationalize that denominator. Go back to primary school when we learned how to do that. And what do you normally do to rationalize a denominator? Well, you multiply the numerator and the denominator. If you see a plus in front of a square root, you switch that plus to a minus. When you're rationalizing, multiply both the numerator and denominator by that minus version. And if we do that, we're going to FOIL out the denominators, right? So we got our first, which is just n plus 1, root n plus 1 squared. So that's going to become n plus 1. We've got our outside, which is going to be a negative root n plus 1 times root n minus 1. We've got our inside terms, which is going to be a positive root n minus 1 times n plus 1. We've got our last terms, which will be root n minus 1 squared, or just negative n minus 1. Because we're rationalizing, this will always cancel the two inside terms. It's kind of the point. And in fact, if we look at what's left over, we've got a plus n there, and we've got a minus n there. So the denominator is really just going to turn into 2 plus 1s, also known as 2. And then our numerator is just left over with what we started, root n plus 1 minus root n minus 1. So at this stage, if we actually simplify, right, we simplify this expression into 1/2 root n plus 1 minus root n minus 1. The question is this a sequence minus one of its neighbors? And the answer is definitely yes, right? Because we're seeing this root n plus 1 and we're seeing a root n minus 1. How does n minus 1 compare to n plus 1? Well, it's 2 less than, right? And we've got root n minus 1 happens to be 2 less than root n plus 1. And so it's this minus 2 here that's saying we've got, you know, our neighbor 2 houses down instead of our neighbor 1 house down. So we've got this situation where we do have a neighbor an minus 2, where in particular we're defining an as 1/2 root n plus 1. Well, if we go all the way back to the statement of the corollary, which lets us solve this, since that k is a 2, this k is going to be a 2. And what's happening on this right-hand side, let's actually expand that out, because it's a definite sum. If we expand it out, we're going to plug in j equals 1. That gives me an max minus an min minus 1. That's going to be the first term when j is equal to 1. And then when j is equal to 2, I'm going to get plus an max minus 1, and we're going to get minus an min minus 2. So it's going to be a collection of two sums of differences where the subscripts, let's recall what our subscripts were from the problem, were a 1 and a 15. So I'm going to put a 15 in for n max, a 1 in for n min, a 15 in for n max, and a 1 in for n min. If I do that in my example, I'm going to put a 15 in for n max, a 1 in for n min, that term was 1 minus 1, a 15 in for n max, that term was 15 minus 1, and a 1 in for n min, that term was a 1 minus 2. So we're going to evaluate 4 terms of this sequence. So that's just going to be evaluated at 15, 0, 14, and negative 1. When I do that, here's my 15, here's my 0, here's my 14, and here's my negative 1. I'm going to evaluate all 4 of those terms. I get root 16, root 1, root 15, and root 0, which root 16 is 4, root 1 is 1, root 15 can't really be simplified, and the 0 stays at 0. Or altogether, if I have my 1/2 out front, that's going to be 3 plus root 15 over 2. Our last example, we're going to go through one more case. I realize this is kind of beating a dead horse at this point, but I want to give a lot of these examples because it does show you how we can actually compute quite a lot of definite sums just by using telescoping. We've got this ratio 1 over n squared plus 4n plus 3. Once again, I'm going to use this idea of partial fraction decomposition, which we haven't learned yet, but we're going to learn very soon. And that'll tell us that actually this ratio 1 over n squared plus 4n plus 3 happens to be 1/2 over n plus 1 minus 1/2 over n plus 3. And we're going to recognize that, well, you always want the bigger one, in this case n plus 3, or farther forward in the sequence. That one's going to go first, so we'll call it a negative 1/2 over n plus 3. And then n plus 1, how's n plus 1 compared to n plus 3? Well, it's really n minus 2 plus 3. And so we see, again, in our case, we've got our original sequence, and then we've shifted our sequence down by 2. We have a difference of those two. In particular, what is our sequence here? Well, it's always going to be the bigger of the two terms. So we've got negative 1/2 over n plus 3. What are our bounds? Well, our bounds have switched to 4 and 12. And so if we write out, this is kind of the definition that the corollary is going to give us, the new version of a summation that we have to compute. Instead of from 4 to 12, we just have to compute it from 1 to 2. But now we've got these shifts by j, and we've put in our upper bound plus 1 is 13, and our lower bound, which is 4. Okay, so if we compute that definite sum, it tells us, well, plugging in j equals 1, that's a sub 13 minus 1, that's going to be a sub 12. And then I've got a sub 4 minus 1, that's going to be a sub 3. I've got a sub 13 minus 2, that's going to be a sub 11. And then I've got a sub 4 minus 2, that's going to be a sub 2. So I've got 4 terms here because this was, unfortunately, a shift by 2. You have to put up with those 4 terms. I'm going to evaluate a12, a3, a11, and a2. And I've got those evaluated down here. a12, a3, a11, and a2. And how do those terms work out? Well, I've got 1/2 over 15, 1/2 over 6, 1/2 over 14, 1/2 over 5. If I evaluate everything out, turns out to be 4 over 35. Okay, so that was definitely a lot of work. I would suggest that, aside from the partial fraction decomposition, you kind of attempt each of these by yourself before really looking at my answers. I would use my answers kind of as a guide after you've tried to evaluate the sum, at least of this, after the partial fraction decomposition. Do it yourself and see if you can understand what that corollary above is saying for telescoping sums. We've also got the second most common technique that students learn when it comes to manipulating sums, and in particular definite sums, but we do have this for indefinite sums as well. This is called reindexing. And it's the closest thing we have for substitution. There's a true substitution which has been reserved for the appendix, and if you look at this reindexing idea as a specific output of the substitution technique we learn in the appendix, which we're not actually going to cover, you do get the answers that we have here. But reindexing is quite important. And all it really says is that we're allowed to shift our subscript. So this is saying we're going to shift the subscript by k. And when we shift the subscript by k, it says that, well, the indefinite sum remains the same. Indefinite sum doesn't change. It's unchanged by a shift. A definite sum, on the other hand, the bounds are shifted. Bounds are shifted in the opposite direction. For a definite sum. So that's what I've done here. You'll notice I've got an an there, there's an n min there, and an n max there. Here I've got n minus k, so there's my shift. Well, the bounds have to pay the price. So if I'm shifting by negative k, the bounds are going to get added k. And this actually is the exact same technique as when you would redo bounds, integral bounds for u substitution on integrals. And so the technique's the exact same here. You would know if you tried to do, let's do a really quick u substitution. Suppose I have f of x minus 3 dx, and I'm going from 1 to 5. And I let u equal x minus 3 because I want to do a u substitution, then du is just 1 dx, but I have to consider the bounds, right? U min happens to be x min minus 3, and so we evaluate x min, which happened to be 1 here, we evaluate that, and we have 1 minus 3. It turns out u min is going to be negative 2, and u max would be x max minus 3, which would be up here at the top, 5, minus 3 would give me a positive 2. And so if I converted this integral, we would have from negative 2 to 2 f of u du. Now, why does that actually look the same? Well, what's actually happened? What has my reindexing been? It's this. U minus is x minus 3, or in other words, u plus 3 is x. And so that's really your reindexing. You've added 3 to the x term here, so you subtracted 3 from the bounds. So that's why it really behaves the same. But it's just important to get used to, hey, if I want to shift the subscript, I have to shift the bounds in the opposite direction. And there's a beautiful proof there, but it's huge. Let's go through some examples of this. So the examples, we can do one example of a reindexed indefinite and one reindexed definite sum. The indefinite is quite straightforward, but let's just say we've got something like n squared plus 1, and we're going to compute the summation of n squared plus 1. And that sum is going to be, the indefinite sum will be n cubed over 3 minus n squared over 2 plus 7n over 6 plus c. Then you can actually compute this summation, which happens to be n squared minus 2n plus 2, using our information from above. So if we know that the kind of the antiderivative of n squared plus 1 is this, then we look here and we see, okay, that's not n squared plus 1, but what is this? This, if I complete the square on n squared minus 2n plus 2, well, you complete the square, you see that it's n minus 1 squared plus 1. Now, how does n minus 1 squared plus 1 compare to n squared plus 1? Well, it's actually just a shift by negative 1, right? I've replaced every n with an n minus 1. The moment I recognize it as a shift by negative 1, I'm just going to say, oh, if I shift, right, this is what summation says, I can shift that by negative 1. And all I have to do is shift this by negative 1. Well, if I shift that by negative 1, I'm just going to shift each of these individually by negative 1. Okay, so that's how reindexing works. If you're just going to use it for your rules, I'll show you how to do that here, right? There it is. A(n minus 1 is capital A(n minus 1, and capital A(n minus 1 is this shift, right? Just replaced every one of these n's with n minus 1. So there's my n minus 1 cubed, my n minus 1 squared, and my n minus 1. And so you can recover your answer just by recognizing that what you're asked to do is a shift of what you already know. I think the reason why most students learn reindexing is actually this following case, which is a definite summation. If I take some definite sums, you can actually combine two, so it's a combine the addition of two definite sums by recognizing that their bounds are initially different, okay? So the bound here starts at negative 2, it ends at 4, the bound here starts at negative 4, it ends at 2. Can we get the bounds to align using reindexing? Yeah, the answer is yes. So what am I going to do is I'm going to take the first summation here and I'm going to reindex it by something called k1. When I reindex that by k1, that means I'm shifting both cases of n by k1, and in fact by minus k1 in this case. Okay, so I've replaced both n's with n minus k1. And I have to pay the price on the bounds here. I'm going to do plus k1 on both of the bounds. There they are, plus k1 on both of the bounds. I'm just going to leave it, okay? We're going to leave it for now. But that is the process of me reindexing this, is shifting both n's by k1 in the negative direction and both bounds in the positive direction by k1. So we're going to leave it there. We're going to do the same thing with our second sum. We're going to shift this by k2. And when I shift the second sum by k2, well, what am I going to do? I'm going to take this n, I'm going to shift it down by k2, so there's n minus k2, and then my bounds need to pay the price of adding k2 and adding k2. And so there they are, that's me adding k2 to both bounds, and then we're going to leave it here for now. And what we're going to do is we're going to try to align the bounds to be the same number. We can combine sums, just like combining integrals, so long as the bounds happen to be the same number. Initially, they're not the same number, but if we look at my shifts, negative 4 plus k2, negative 2 plus k1, 2 plus k2, and 4 plus k1, I'm going to want those to be equal to each other. And I can choose any k1 and k2 to make them equal to each other. Let's just make them both 0. Let's make the lower bound 0 in both cases. So if I scroll up a little bit, I can say, what if I chose k2 to make that be equal to 0? What if I chose k1 to make that be equal to 0? How could I do that? Well, negative 2 plus k1 is 0. That means k1 should be 2. Negative 4 plus k2 is 0. That means k2 should be 4. That's what I say down here. K1 should be 2 and K2 should be 4. This is totally up to you. You get to choose how to align these sums together. There are infinitely many right answers here. You just need to actually combine them. And when we set K1 equals 2, that means we're going to shift our first one by 2. So we shift the first one by 2, both the bounds get added to 2, and then the actual inside sequence gets subtracted by 2. And that's what I've got there. And then I recompute the bounds. 4 plus 2 is going to be 6, and negative 2 plus 2 is going to be 0. I do the same thing with the second sum, which is when I have k2 is equal to 4. And so I'm going to take and shift my index by 4. That's going to be n minus 4 in the power here. There's my n minus 4. The bounds pay the price of plus 4, so I've got negative 4 plus 4 in the first bound. That's going to become 0. And 2 plus 4 in the second bound. That's going to become 6. So after all that work, you can do a lot of this in your head if you want to. Basically say, I started with this one starting at negative 2 and going to 4. This one going from negative 4 to 2. I need to shift both of them to start at 0 and end at 6, to start at 0 and end at 6. And at this point, if we look at these two sums, they can be added together because the bounds align. So now that I've shifted my bounds here to align, I can kind of, this is the opposite of linearity, right? Where I'm going to take this summation and I'm going to pull it out. Now I've combined my summation I only have one copy of that, and it kind of sees everything added together. Now, it might not be clear why I would ever want to do that. It's really, you have to get into another math class called Ordinary Differential Equations and Power Series Methods section of an Ordinary Differential Equations course to see why you would really want to combine sums together. But you can imagine it's slightly useful. Sometimes terms would cancel between the two sums, and so you can make your life easier. Okay, and then we're over here at the first power rule for summation, but actually I'm going to save that for the next video. This one's been a little bit long so far, so I'm going to leave it at that for today. We'll get a lot of practice in and then get excited for this first power rule. It's really, really ugly. We're not going to spend too much time on it because it's ugly. There are other power rules as well. If you remember the following factorial, we'll also talk about summation by parts. See you then.